I'm sorry. A number of my team that work actively in both GPU and fine-grained parallelization showing up in terms of Z on phi. I'm getting a little echo here. Too close. Oh, sorry. All right. Okay, so NOAA Earth System Research Laboratory. Non-hydrostatic NIM, just very briefly, this is a hexagonal icosahedral grid. It maps very well for global domains. In particular, the traditional latitude-longitude models have problems near the pole and have to do all sorts of maneuvering in order to handle instabilities that are happening there. It uses an indirect addressing scheme in the code that permits very concise, compact, efficient performance. And you see here that what that translates to here is, oh, I'm weak here. Hang on. Yeah, boy, that is weak. Okay, so what you see typically is 3 dimensions for a traditional lat-long model. Maybe K, which is your vertical dimension on the inside for dynamics, is appropriate. With the NIM, we just have 1, and it's an index that becomes a reference into an array that identifies the neighboring points. And this actually has a number of advantages. I'll share with you a little bit of that later. This code has been parallelized and is efficient running on the CPU, the GPU, the mic. We use directives to do that. OpenMP for the CPU. GPU, we use a compiler that I developed called F2C, but we're also using PGI and Cray. I'll report just a little bit on that. The mic, we're using OpenMP plus extensions, and then we have our own directive-based scalable modeling system that's used for the shared distributed memory parallelism, which is many of you think of as MPI, but effectively we just put directives into the Fortran source code and it runs everywhere. The physics, we have 2 physics packages, the GFS, which is the operational global forecast system run in U.S. National Weather Service, and that's used for hydrostatic scales. That's what so far that physics has been tuned for. We're also working with the WRF ARW physics, which is much more capable of going to higher resolutions that we plan to do with this NIM model. We have done OpenMP parallelization for the GFS, and we're working on right now the GPU parallelization for the WRF ARW. The model is under active development. We're right now testing at between 30 and 15 kilometer resolution. We have made some runs at 7.5 kilometer resolution. We expect 3.5 kilometer resolution for this global model in 2015. At 3.5 kilometer resolution, there's 42 million of these grid points that you see here in this view of the icosahedral grid, and it uses 96 vertical levels. So one of the rather daunting things is to think of how we're going to manage all the data that a model of this resolution will produce. At 3.5 kilometer resolution global, we run the model for a 7-day prediction, and we produce output every 3 hours. 10 variables is a minimum. Once we start including chemistry, which is a plan, there could be ocean and moisture variables, which would include in here. We go well beyond the 9 terabytes that we're projecting here for a single model run at this resolution. We're also designing this model to run for climate scales, regional climate scale prediction. 100-day predictions produce about 16 terabytes if you produce files every day. This is daunting to think about how we're going to handle and manage the organization of files so they can be efficiently accessed, where we're going to store and access this data and how, and what we'll do about displaying data in such a way that it can be used in a real-time forecasting scenario. The belief right now, and I think it's shared by many, is to avoid moving the data. So perhaps this is a cloud-type solution or similar, where you have the data resident in one place and then you bring the processing to the data in order to do things such as analyze or visualize the data. The idea with visualization, if you're doing such a thing remote, is you're obviously not going to move 9 terabytes of data around very quickly. So we're thinking in terms of just sending the pixels to display the data instead. And I'm going to briefly segue to what we've been doing recently with visualization. We have a GPU-based visualization which is using Unity 3D gaming software, which takes the FIM model output. So the FIM is a predecessor to the NIM. And here what we show is let's see if I can get this to, I might have to, oops. I think I have to go up here and show this. It's a little movie. Doesn't seem like, oh, there we go. Okay, so what you see here, this is a case of Hurricane Maggie, which began in the, oh, it's not going. What you can see here is the beginning of the hurricane that's happening there. And are you able to get this to move? Yeah, you can see that. So you can see, yeah, can you make that full size? So what this is FIM model output produced every hour for this simulation, and it's showing cloud, which looks a lot like what you'd expect from a satellite. The resolution of this model is not sufficient to resolve clouds. This is a 15-kilometer resolution. The reason we're going to 3.5-kilometer resolution with the NIM is for the cloud resolving capabilities that are needed to better predict the weather. Moisture is a very big component of that. Are you having, should we? I didn't know movies were going to be so much trouble.
Once you bring up the animation, I can just drag it over.
Oh, I just went over here to, oh, doesn't seem to be working. You know, I think I'm going to have to pass on this.
Okay.
Yeah, I'm going to just move on because I'm running out of time. This was meant to be a small diversion. The idea here is that this is a way in which we initially did work with Google Earth, and it was much, much too slow. We couldn't display the number of points we needed. The performance was not very good, and so a GPU gaming engine was the way in which we envision forecasting systems in the future. Now I'm not going forward at all.
You are here.
Okay, so are we good now? Yeah, okay. So this has been a team effort from the very beginning in the NIM. The computational scientists, along with the domain scientists, have been working together to design it for GPU and especially fine-grained. The early work was before Intel had a competitor to the NVIDIA GPU, so we were focused primarily on GPU, but they map very well. At that time, there was a compiler that I developed to do just the transformations from Fortran into CUDA. And 2009 through 12, the model was being developed, and the focus was on single GPU performance. And in 13 and 14, we have done quite a lot of work on parallel GPU runs for Titan, and we've done similar work with the TAC for the Xeon Phi performance and scalability. Single source code, as I said, for CPU, GPU, and mic, and this is striving for best performance on all architectures. And this is a challenge, and I think it's an ongoing research, is how to design your code such that it can be capable of producing very good performance on all architectures. Oh, this is annoying. All right, I'm going to go up here. Where are we at? I'm missing a... All right, so this is an example of code, typical code. There's, in blue are the F to C ACC directives. In red are the openACC directives. They're quite similar in placement and meaning. In the ACC region or parallel, we are saying that we've got 96 vertical levels. This is the thread dimension, and 10,242 horizontal levels. This will be what would run over a single GPU, and we do various things. When we break up a domain across many GPUs, we effectively end up with the same number of points. We use parallel or gang for the horizontal dimension in this example, and loop vector or do vector for the ACC, F to C ACC. So quite similar, and it turns out to be quite simple to make the code work with openACC. Let's see if I can, all right. So when we get all done with running everything on the GPU, we make the arrays resident on the GPU through the duration of dynamics. The results we require to be bitwise identical to the CPU baseline, and we've been able to demonstrate that with PGI, Cray, and Intel with the F to C compiler. Am I okay? It didn't advance? That is really annoying. Okay. Maybe it's because I developed my presentation on a Mac, and Intel doesn't like Macs. I know. All right, can you advance the slide? No.
He's got to get his 5 minutes back here.
I deserve 5 minutes. Technical problems.
Well, now let's see how good a speaker you are with no slides.
Okay, so what you see here is a comparison between a CPU baseline run and a GPU run. And we do this for the PGI in this case, and it's showing that the number of digits of precision, 8, is exact. That's what we're looking for in every step of the way. So this helps us identify where there would be parallelization bugs or potentially other bugs where correctness is not demonstrated. We won't proceed until we're able to do that. Now, in the case of dynamics, we've got a single instance of the Fortran power function that we execute on the CPU in order to get this bitwise exact capability. In the future, can we go on to the next? Oh, there we go. It's working. When we get to physics, and we're doing this now, is that we've run into a lot of intrinsics, and intrinsics are not reproducible, bitwise reproducible. And so we're stuck with trying to do measurements where it's not so easy to figure out whether the model is going to have parallelization bugs or instabilities that show up because of errors that we've introduced. So what we like to do is have some sort of slow, bitwise exact intrinsic routines that we can incorporate so that we can get back to this exact solution, allow us to do direct comparisons between CPU and GPU. Right now, the execution model that we run on Titan is at the top. We run dynamics. We do some communication to the CPU, run physics, and then do communication back up to the GPU to continue doing dynamics. This isn't where we want to be, and the work right now is in doing the physics parallelization, so everything is running on the GPU. We do recognize that there is the CPU there, and we could take advantage of that capability if we ran in symmetric mode, which is a term borrowed from the Xeon, the Intel mic, is they have a symmetric mode that allows you to take advantage of the CPU and GPU. And basically, you just assign MPI ranks to the CPU and the GPU, and they all work together quite happily. So that will be a next step for us in the future. We kind of think that, we hope that this isn't necessary. We think future generations of GPU will be able to do it all, and we won't need the CPU other than for access to the file system. We'll see. Performance on Kepler, so this is strong scaling, showing number of processing elements processing nodes out to 10,000. This was done on Titan. And its SandyBridge is showing up here in red. The K20x is showing up in blue. And you see here forecast days per compute hour. The numbers here, what you see here is a little smaller scale, so you can see what's going on here. It's a little bit like what Thomas has talked about earlier, is if you have enough work for the GPU to do, then it's very efficient. If you start running into this area here, where there's less and less work, the GPU is sitting idle because there's not enough work queued up, then the SandyBridge runs faster. It doesn't run faster here in a node-to-node comparison, but it is running more close to the results that you get from a GPU. So we're very happy with these results. We think that our sweet spot is going to be somewhere in this range for real-time prediction for the NIM when we incorporate dynamics as well, physics as well. Where we were 2 years ago was this red line here, the lower point, which was we were being consumed by a lot of time to do communication between the GPUs. And so the focus of work, particularly by Jacques Middlecoff, was to improve performance here such that we're up at that blue line you see there. So that effectively was communications was taking over 50% of the runtime, and we're down to now 14% of the runtime. That's primarily happened in two areas. We've used GPU mapped memory, and that got us 2.4x improvement. And we combined all pack and unpack routines into a single kernel for each MPI exchange. And I'll explain this a little in the next couple slides. That gave us 2.9x. It allowed us to overcome the penalty for kernel startup, the GPU. And that adds up pretty quickly when you've got not a lot of work for the kernels to do and a lot of data movement. And the way that works here is that if you have a processing element you see on the right, P1, and it's got to communicate with its neighbors 2, 3, 4, and 5, you have to take data from the interior up at the top there and put it into a MPI messages ready to communicate MPI messages to these processors, neighboring processors. And you do it with this pack, and it's a kernel in the GPU. So for each one of these, we have a kernel that is representing the pack necessary to do, prepare the data for MPI exchanges, send and receive. And then the data on the other side is unpacked, and you have all these kernels that are doing all this work and taking a lot of time. So what we did was combine all of those into a multivariable pack, which allowed effectively 11 or more variables that were being done individually to be packed all at the same time. This overcame a fairly big problem with kernel startup and gave us a big benefit. How are we doing on time? All right. So this is my second to last, or might be my last slide. So some work has been done recently with openACC compilers running on the latest version on Titan, which is 14.1 for PGI and 3.2.8 for Cray. Some earlier work was done with CAPS, and I haven't been able to get back to that, but the intention is to use the CAPS compiler for evaluation as well. Been able to identify and report some bugs to PGI and Cray, and been working actively with those companies to improve those compilers for the NIM. I've noted some inconsistencies between the vendor implementations of openACC. I'm going to discuss a little bit of that at our little lunchtime meeting. Right now, I'm noting that performance is currently slower than FTC, but it's too early to know whether there's issues with how the openACC directives are being used or whether there's some improvements that need to be made in the Cray and PGI compilers. Again, CAPS is another target for this. And I think I am going to stop there, yes. So that's it.
Thank you, Mark.